Hi, can everyone hear me?
Hello, sir. How are you?
I'm good, I'm good. How are you?
I'm very good. I have one more student that we are waiting to join. Give me a second to call him. I don't know why he's not connected yet.
Sure, no problem.
Give me 2 minutes.
Yeah,
Hi, George. Have you introduced yourself, George?
I'll
Hello,
just,
I am
hi.
your I am a student in Cyprus,
Okay, your name is George?
and I am a student from Cyprus. I am 16 years old.
Right. Welcome. We'll do some classes and some problems and try to improve.
Okay.
Right now, you have appeared in maths competitions before?
Yes, I went to a JBMO once and then IMC.
Okay, great. Okay. Let's also wait for Philip. Philip, I think, is joining.
Uh-huh.
Yes, Philippos. That's perfect. Okay.
Right. My name is Ashish. I'm based out of India, by the way. If you guys don't know, I have been teaching for Olympiads, both maths and physics. Have been teaching for the last 5, 6 years. Uh, and this is a first for me. It's like some of you have actually represented your country in competitions, right? So that will be exciting for me as well. I would love to help you guys. Right now, with Andreas, we have decided that we'll just start off with one class for now per month, and then we'll see if you need any more help, then I can pitch in with more classes. Okay?
Yes, thank you, Ashish. You can start whenever you like. You can do the lesson as you wish. You can ask the students if
Right,
they find the question easy or they prefer more difficulty and things like
right,
that. And you
right.
can adjust the lesson accordingly.
Sure.
All right. Thank you very much.
Okay. Philip is there, right? Can you hear me? You can unmute yourself, Philip. I hope I'm saying your name correctly. Okay,
Philip says that he cannot unmute for a
okay,
reason.
okay, no problem. It's fine. As long as you can hear me, it's okay, right? I hope you can hear me clearly. Okay, okay. Fine. So what we will do today is learn about some proof techniques. I want to focus in today's class on the technique of induction, and we will learn about types of induction and how we do mathematical induction using some problems. So perhaps you'll be familiar with problems like this, but if not, we will discuss the solutions in class. And I want you guys to try the problem right now, and then we'll discuss if there is some difficulty, right? So the hint is that we'll be using induction. After that, we'll do more specialized types of induction, but for now, this is the first problem. So let n be belonging to natural numbers. I have put a star because it starts from 1. So it's the positive natural numbers. We have to prove that after removing any 1 cross 1 square from a 2 power n cross 2 power n grid, the remaining part can be tiled with L-shaped tiles. I will show you the shape of the tile. This is my L-shaped tile. Notice the area of this is 3 units. There are basically 3 1 cross 1 squares in one L-shaped tile, such that there are no gaps and no overlaps. So think about the question for a moment and tell me if you understood the question, if that question is clear. And I hope you know about the meaning of the word tiled. If anybody has an issue with the question, please tell me. If you don't understand the question, I'll try to explain it. Basically, you have a square. This square has size 2 power n and 2 power n. So this length is 2 power n and this length is 2 power n. The question is saying that if you remove any one square from it somewhere, let's say I remove a 1 cross 1 square here, the remaining shape can always be tiled or can always be filled using the L-shaped tiles that we discussed. You can always fill the remaining shape with L-shaped tiles. George, is the question clear?
Yes. Wait, can you put the L-shaped tiles, like, can you rotate them and then place them?
You can place anywhere. The L-shaped tiles are set. You can rotate them and do whatever you want with them.
Okay.
Like you can place it like this, for example, one L-shaped here, and the second one can be put like this, right? Do you understand what I'm saying?
Yes.
Basically, this is a gap. There is a 1 cross 1 thing that has been removed. I have to prove that somehow I can fill the remaining shape with L-shaped tiles. And the L-shaped tiles have size of 3 units because they are built of 3 1 cross 1 squares. I would suggest that you think about maybe like starting with some small squares and think about, is it possible for you to build it? And the technique that will be used to prove is induction. So that is a hint for you. Let me know if you are stuck somewhere, if you're thinking of something, and if you have any issues. Philip, you can type in if you are making any progress or if you're stuck somewhere. Let me know if there is any question, okay? George, any progress, any ideas?
I think I know the answer, but I'm not sure how to prove it.
Tell me what you have thought so far. Tell me.
When I tried to do this and
Hmm.
I tried with 1 by 1, then
Hmm.
2 by 2, then 4 by 4.
Mhm.
I always found that when you remove a tile from
Right,
the central
right.
square,
Uh-huh.
you can actually solve it. Then you can actually find a way to cover all the shape, but I'm not sure how to prove it.
Okay, so one thing is obvious that we cannot take 1 by 1 case because that will be n is 0, right?
Yes.
And the question said that n should be positive naturals, right?
Yes.
So we start off with 2 by 2, and you can see that if you remove any tile, automatically this is a L-shaped tile, right? From a 2 x 2 square, if you remove one of them, automatically it is filled by one L-shaped tile, no?
Yes.
So that case is trivial. It is obvious, right? Correct. So what we have to think about, if you think of a 4 x 4 shape, right? Let's do a 4 x 4. This is a 4 x 4 square. Now tell me, suppose I remove a tile here. This is removed. Are you able to figure out how to fill it with L-shaped things?
Yes, I think.
One tiling is this, right? One L-shaped tile is this. One tile is this. One tile is this. One tile is this. One tile is this, right? Does
Yeah.
everyone see that you are able to fill it? Right. Okay. So suppose I had shifted the position of this for this one. I'm going to shift the square's position. Let's say now my square is here, the one that I remove. Can you still find the tiling? Okay. One of you, Philip, I think is able to find. Just think about it if you're able to find it or not. We
Yes,
can.
I think I can find.
This is one. This is one. This is one. This is one, and this is one. Yeah. Can you see we are able to find it for 4 cross 4? No matter where you place, you'll be able to find a way, right? So now what we need to do is to construct a proof of it, right? That's the tricky part, right? George, are you understanding what I'm saying?
Yes.
So for a proof, I would suggest that you start by induction. This is the power of the method of induction. No matter, even for a weird question, we can use induction to do it. So first of all, do you know the method of induction? We have to do a base case first, right?
Yes. I think you start with the most basic case, like here it's a 2 by 2.
Right,
Then you make an assumption
right,
that when n is equal to k,
right.
and do it, and then you do the induction step where you try to prove that 2 to the power of k plus 1,
Correct,
that
correct.
n is equal to k plus 1. You can do it.
Right. So you can see here clearly that base case is over, right? Base case is a 2 cross 2 figure. We know it can be tiled when you remove one of them, right?
Yes.
Base case is done. So now what we will do is we'll make our induction assumption. The assumption is that the proposition is true for n is equal to k, which means that if I have a 2 power k cross 2 power k square, after removing one square, it can be tiled. It can be tiled using our L-shaped tiles. That is my assumption right now, correct?
Yes.
Now we have to prove it for 2 power k plus 1 cross 2 power k plus 1 situation. If we can prove it for this, then we are done, right?
Yes.
So what I would give you a hint is we have to use this assumption somehow, no? So the hint for you is you can easily break up your square when it is 2 power k plus 1 cross 2 power k plus 1. You can break it up into 4 2 power k into 2 power k squares. Do you understand what I'm saying?
Yes.
Because each side will be how much? This has to have 2 power k plus 1 length, right? I can say that if I divide that by 2 on both the length and the breadth, this should be 2 power k, this should be 2 power k, right?
Yes.
So my 2 power k plus 1 cross 2 power k plus 1 big square can be broken down into 4 smaller squares, right?
Yes.
And now I will give you 2-3 minutes to figure out the step, how to prove it. It is possible to do it, and I think you guys can figure it out. We already know.
I think I know how to.
Yeah. Think about it and tell me if you're sure.
I think um, when we make the square that needs to be removed
Right.
for each of the four parts
Hmm.
to be the one in the middle,
Hmm.
2 by 2, then we're left with 4, and we can add one more tile, and 3 of the 4 will be covered. So we only need to, in the 2 the power of k plus 1 case, we can also only remove 1 and make it.
Okay, right now maybe you have understood it, but it is not very clear to me. Like you have not been able to explain it to me really well. So think about it a little more. Think about how you would explain it to someone, right? The method that you have thought of, just think about it a little more. You have to clearly explain it to me so that I can also understand it. So what I'm saying is I have removed one square from here, let's say. What is the next step? Think about it for 2 minutes. I'll be back in a minute. Just give me a second. Yeah, okay, I'm back. So, George, do you have a next step here for what to do? I have removed this random tile from here.
When you remove the random tile, we can assume that that square can be tiled from our assumption.
Right, this square, yeah, it can be tiled.
Yes, after removing one square.
Correct. But we don't know yet about the others, right?
My idea was,
Huh.
since we can remove one tile and from each of the squares, and then they can be tiled,
Correct.
and it doesn't matter which square we remove it from. Then we can choose the tiles from each of the squares to be the tiles of the 2 by 2 square in the middle of the whole square.
Okay. So you are saying these, right?
Yes, and yes, and
Correct. You have the right
also,
idea.
and also for the other one, for the bottom left one, and if we
I have already made 3 tiles on the center. Can you see? I have made one tile here, one
okay,
tile
yes,
here, and one tile here, right?
yes, and then we can use one more L tile, and
Right.
yes,
So basically the idea is that if I have removed one tile from here, automatically this portion can be tiled, right?
yes,
With L's, right? So
yes,
the idea is from whichever square you have removed this tile, other squares we'll remove one here, and one here to make an L.
yes,
If you remove an L-shaped tile from the center, the remaining squares 1, 2, and 3 can automatically be tiled with remaining L's, right?
yes, from the assumption.
From the induction assumption. And therefore, what we can say is that this is also an L, right? This is an L.
Yes,
So automatically the whole figure is tiled with L's now, right?
yes, right.
So basically, we have proved that 2 power k plus 1 and 2 power k plus 1 can also be tiled with else. Now, this doesn't depend on from where we remove the square. If I had removed a square from here, I would have removed one L like this.
Yes, it doesn't matter where we put the fourth because
Right. So we can say that as long as you remove one, you can always fill up the rest with else.
yes.
I hope it is clear for Philip also.
Yes.
Okay, cool. Okay, so this was one example of a question which it seems like on the face of it, when you start the question, you don't know how to begin, right? But it is actually pretty easy with induction. I hope everybody can appreciate that. And the key idea in the previous question was to work with one or two base smaller cases. And when you get the smaller cases, you will get the central idea of the induction. So keep that in mind. I will come to a next problem here. We say let x and y be real numbers satisfying that x plus y, x square plus y square, x cube plus y cube, and x power 4 plus y power 4 are all integers. We have to prove that x power n plus y power n is an integer for any n belonging to positive naturals. This is not too difficult, and it is obvious that you have to use induction here, but I want you guys to try it out. By the way, you should be aware that sometimes you can change the step size of the induction. What do I mean by step size of the induction?
Yes, I think I know. I think you're talking about strong induction, where in the base step we prove that we can prove that there are four, and then in the assumption we can assume for
Right,
four numbers like n is equal to k minus 2, k minus 1, k,
right.
and k plus 1.
So you understand the idea of step size. The idea is usually we use one step, right? Pn implies Pn plus 1, right? However, you can do it with 4 also, you can do it with 2 also. For example, here I can do it like this, that base case is n is equal to 1 and n is equal to 2 is true. And induction step, I need to say that if Pn and Pn plus 1 is true, I need to prove P of n plus 2 is true. Here my step size is 2, by the way. Okay. You could even do a step size of 4, right? So anytime you do 2 base cases and 2 assumptions in the induction step, the step size is 2, obviously, right?
Yes.
By the way, this is not the same thing as strong induction. Strong induction is assuming that all the steps before n are true. Strong induction says that
Okay.
for all k less than equal to n, the P of k is true. And from there, I need to show that P of k plus 1 is true. That is also a form of induction. There you assume that all the steps before are true, and from there you have to go to the next step. I hope everybody is understanding what I'm saying. Okay, so here you can try whatever form of induction you want. I would suggest use a step size not equal to 1. Don't use the step size 1. It will become a little hard if you try to do step size 1. But you can try it, like try it out, see if you can prove. Let me know if you're making any progress or if you're stuck somewhere. So what we have here, we know that P of 1 and P of 2 is true. Basically, our P of n is x bar n plus y bar n. And we can say that x bar n plus y bar n is an integer. That is our statement for P of n. We know that P of 1 and P of 2 are integers, right? We actually know that P of 3 and P of 4 is also true. Correct?
Yes.
So base case is already done. My induction step with a step size of 2, we will say that if P of n and P of n plus 1 are integers, we need to show that P of n plus 2 is also an integer. So here the assumption is that x bar n plus y bar n and x bar n plus 1 plus y bar n plus 1 are integers. And from there, I want to prove that x bar n plus 2 plus y bar n plus 2 is an integer. So think about this part. It is actually pretty easy to express this in terms of the others, right?
I think I did.
Tell me how?
First I did x plus y to the square,
Mhm.
and then minus x square plus y square in brackets.
Correct. So that tells us 2xy belongs to integers.
Yes.
Mhm.
So xy, no, wait, I thought xy is an integer, but it's not.
That is an assumption. That is what we actually
Yes.
have to prove. That's the key step. If you assume xy is an integer, obviously it's over.
Yes.
So I will continue with what I am saying here. It will boil down to the same thing that you are saying, Philip. So doesn't matter. So what I'll say here is x power n plus 2 plus y power n plus 2 can be written as x plus y times x power n plus 1 plus y power n plus 1 subtract xy x power n plus y power n. You can easily see that this will give us the same thing. I hope this is clear to everyone.
Yes.
So we already know by assumption that this is an integer, this is an integer, this is an integer. So if I need to prove that the left hand side is an integer, all I need to show is what? Xy is an integer, right? If I can prove that xy is an integer, then I will be done, no?
Yes.
George, are you understanding what I'm saying?
Yes.
Sure. So now our problem becomes prove xy is an integer, because then we'll be able to complete our induction step. So for that, we will now look at what Philip you were doing. So we know that x plus y and x square plus y square are both integers. So by taking the difference of this, we know that 2xy is an integer. 2xy is an integer. So obviously our job is to do what? We have to prove that xy is an integer. Prove xy is an integer. So right now, we are going to do what? If xy does not belong to integer, then we know that 2xy is equal to m, where m is an integer, right? And m must be odd. Do you understand that m must be odd? Because if m was even, xy is automatically an integer.
Yes.
So we are getting xy should be m by 2, right? Correct?
Yes.
And now, since we can also write x square plus y square belongs to integer and x power 4 plus y power 4 also belongs to integer. This was given in the problem. I will repeat the same step, but this time I will have x square plus y square whole square minus x power 4 plus y square y power 4. This will give me 2x square y square, right?
Yes.
And we know that this also should be integer because these two are integers, right?
Yes.
Which means that 2 times m by 2 whole square belongs to integer. So that is m square by 2 belongs to integer, right? Correct?
Yes.
M square by 2 belongs to integer means m must be divisible by 2 then, right?
Yes.
2 divides m, then only this can be an integer, no?
Yes.
But that is a contradiction because now we are getting m is even. We here said that m must be odd, right?
Yes.
Why did we say m is odd here? Because if m was even, then xy is automatically an integer, right?
Yes.
Yes.
If m was even, xy would have been an integer. So if xy is not an integer, then m must be odd. And if m is odd here, from the square thing, I'm getting that m square by 2 is an integer. And m square by 2 is an integer means m is even. So this is a clear contradiction. So that means our assumption is wrong and xy actually belongs to integer. And if xy belongs to integer, we are done because we have proved the induction step now. Is it clear, everyone?
Yes.
Okay, so I think this was doable. Both of you would have gotten it, I think. You just have to spend a little bit of time and take some cases. Okay. Tell me if the problems are becoming too difficult or too easy. You need to tell me because right now I don't know you guys so much, right? If you feel like it is too easy, then I will go to harder problems. And if you feel like it is too difficult, we'll do something simpler. Is it clear, everyone?
Yes.
Okay. So the third problem is this one. Prove that there are no rational numbers x, y, and z satisfying x square plus y square plus z square plus 3 times x plus y plus z plus 5 is equal to 0. So this problem will introduce a very important idea. You might have seen it before, but it's a very important proof idea. I won't tell you because it will ruin the problem. First of all, you need to simplify this expression a little bit to get any sense of the question. We can see that the expression is symmetric in x, y, and z. There is no difference in the x, y, and z variables, right?
Yes.
So whatever happens for x, similar things should happen for y and z. What I would recommend is, since it's an equation with 3 variables and there is only one equation available to us, it's not like we can directly solve it unless there are some powerful conditions, right? Some constraints, right? Do you understand what I'm saying? If there are
Yes.
3 variables with one equation, you can't really solve it, no? Unless you know something really special and really nice. An example of that thing could be if there are perfect squares and all, right? If something like this happened, then maybe you can solve it, right? So what I would recommend is try to complete the squares here. A nice and easy way to do it would be to multiply by 4 everywhere. You will get something like this. And what you can write here is, you can add a +9, a +9, and a +9, and subtract a 27, right? Is everyone understanding what I'm doing right now?
Yes.
What I'm doing is I'm making perfect squares. Hopefully that will help me in the problem. And I have used up all of these terms. I have a +20 minus 27. So it becomes a 7 on the other side, right? So basically we have to prove that there are no rational numbers x, y, z which satisfy this equation. I have just changed my equation a little bit. This is a better equation because we can see patterns and we can see squares everywhere. There is no mixture of terms. This is my situation right now. And here I want to show that there are no rational numbers x, y, z. No rational x, y, z which satisfies this equation. So think about it. Like if there were rational xyz satisfying this, then could you write this as a a square plus b square plus c square is equal to 7m square sort of equation where a, b, c, and m are positive integers. Or at least not a, b, c, just m is a positive integer at least. Think about it for a moment. If x and y and z were rational, you could write it as p1 by q1, p2 by q2, p3 by q3, where p1, p2, p3, q1, q2, q3 are all integers, right?
Yes.
And if we were able to do that, you would get that you'll get something like this: 2p1 by q1 plus 3 whole square plus similar terms 2p2 by q2 plus 3 whole square and so on is 7. And if you work it out a little bit, you will realize it will be some integers square by q1 square and some integer square by q2 square and again some integer square by q3 square is equal to 7, no? Do you understand what I'm saying right now?
Yes.
What I'm actually saying is after taking LCM, the LCM would have been q1 square, q2 square, q3 square. You can bring the q1, q2, q3 on the other side and you can say that this is q2, q3, 2p1 plus 3q1 whole square plus q1, q3, 2p2 plus 3q2 whole square plus another third term like this square is equal to 7 times q1, q2, q3 whole square. Are you sort of understanding what I'm saying?
Yes.
Basically, I'm saying that it will be like this: a square plus b square plus c square is 7m square, where a, b, c are integers. And m is also an integer and m has to be a positive integer. Basically, all four a, b, c, and m are integers. That has to happen if the rational numbers x, y, z were satisfying this equation. Can you see that we are guaranteed that all of these are integers? This is an integer, right? I hope you have followed so far what I have done. I am saying this equation if it has rational solutions, if it has rational x, y, z as solutions, it is equivalent to this equation where a, b, c, and m are integers. I don't care about the particular value of a, b, c, m right now. And obviously, m is positive. We are taking m as positive. We know we have to have m greater than 0 actually.
I think I found it.
What? Tell me.
If we do mod 7,
Right.
a square can be 0, 1, or 4.
Uh-huh.
And if you and it's impossible to get 0 mod 7.
if you do mod 7, a square can be, you are saying that there is a contradiction.
Yes.
It might be possible though. A square can be what? 0, 1, 4, 2. Mod 7, what is the possible values of a square?
0, 1, 4, and 2.
2, and then what happens when you do 4 square? It becomes 7. So that is 0. 5 square is 25. So 4. Okay, these are the 4 possibilities, no?
Yes. I made a mistake. I thought
Right,
you
right,
couldn't get.
right. So it's fine to keep thinking. What we need to show is a contradiction or some way that it is impossible, right? So what I would tell you here is the idea of infinite descent. Have you heard of this term ever? Infinite descent, have you heard of it?
No.
Okay. So the idea is this, that if for positive integers a, b, c, m, I have a result. I have this result. If from here I can prove that there is another solution a1, b1, c1, m1, where that also satisfies the relationship, and now m1 is less than m. So basically every time I have a solution a, b, c, m, I can make a smaller solution where m1 is less than m. If I can prove that, then every time I can keep making smaller solutions, no? Where n2 is less than m1, right?
Yes.
But if there is a sequence of positive integers, it cannot be an infinite sequence. No, if it is a sequence of positive integers, there will be a minimum term after which it will become negative, right?
Yes.
So whenever you can prove that from one solution, you can make a smaller integer solution, that basically means that that sequence cannot go on forever. That means it's a contradiction, because right now it is an infinite series of solutions you will get, no? But there is no infinite series of decreasing integers. If you have a series of decreasing integers, it is always going to terminate, after which the integers will become negative, right?
Yes.
So what we will do here is we'll try to find a decreasing sequence of positive integers m0, m1, m2, which will lead us to a contradiction. So what I want to say is, if I have a square plus b square plus c square is equal to 7m square, and here a, b, c, m naught are integers and m naught is positive, I want to show that from here I can create a new solution a1, b1, c1, m1. From here I can create a new solution a2, b2, c2, m2, and I always have m0 is greater than m1 is greater than m2. And if I can prove that I can keep creating solutions like this, I will have what? An infinite sequence of integer solutions, right? Decreasing integer solutions. But it is impossible to have an infinite sequence of decreasing integer solutions where the integers are positive always. You will not have infinite of them, no? You will cross 0. Correct?
Yes.
So that method is called infinite descent, because you are decreasing the values and making sure that you are always positive. However, ultimately in the problem, you have to think of modulus only, what you were thinking, but you have to be careful there. So let's think about it. If you have a square plus b square plus c square is equal to 7m square, we'll take two cases. Let's say one solution is m0 square. Here I'm taking, this is my first solution where it is m0. If m0 is odd, then m0 square is going to be congruent to what? Modulo 8. Think of modulo 8. If m0 is odd, you can have 1, 3, 5, 7. 1 square will be 1, 3 square will be 1, 5 square will also be 1, and 7 square will also be 1. Can you see that it is 1 mod 8, m0 square?
Yes.
So basically, then 7 m0 square will be congruent to 7 mod 8. Correct?
Yes.
And a square plus b square plus c square has to somehow be equal to 7 mod 8. And what are the possible values of a square, b square, c square mod 8? It could be 0, it could be 1, 2 square would be 4, 3 square would be 1 again, 4 square would be 16, so that will be 0. 5 square is 25, so that is 1. And is there anything? 6 square 36 is 4. So 49. Nothing else, right? These are the possibilities, no, for mod 8.
Yes.
So if I add a square, b square, 3 square, 3 terms like this, what are the possible moduli I can get? I could have 0, 1, 2, 3, 4, 5, 6. I could never get a 7 by adding 3 of them. I could get a 6 by doing 4 and 1 and 1. I could get a 5 also. Do you see what I'm saying?
Yes.
Can I get a 3 though? Wow, 1 and 1 and 1, right. Is everyone understanding that the left hand side cannot be anything other than these 7 options?
Yes.
But the right hand side is 7 mod 8, right?
Yes.
So that proves that m0 cannot be odd. M0 cannot be odd. Right? So
Yes.
now we come to the case where our m0, the first solution, m0 is even. And if m0 is even, we basically have a square plus b square plus c square is equal to 7m square, m0 square. But m0 square is divisible by 4. So it is congruent to 0 mod 4, right? Correct?
Yes.
But when you do squares of an integer modulo 4, you should know that it is always 0 or 1 mod 4, right?
Yes.
So, how is it possible for them to add up to 0 mod 4? 3 of them. One possibility is 0, 0, 0 mod 4, right? Correct?
Yes.
But if even one of them is 1, you can never get a 0 mod 4, right?
Yes.
Do you understand what I'm saying? Even if one of them is 1 mod 4, it is not possible to end up with a 0 mod 4 then. Right? Because you will get
Yes.
something like 100 or 110
yes.
or 111, right?
Yes.
So basically what this means is the only way to have a solution here is if a square, b square and c square are also 0 mod 4, which means that a, b, c are also even, right?
Mhm.
Correct, no?
Yes.
So the solution is coming that if m0 is even, ABC must also be even, right? Correct?
Yes.
And when m0 was odd, there was no solution. Correct?
Yes.
So if I start off with this solution, and I know that there is only even number solutions, so obviously this means that A is what? 2 times, we can say that our solution is A0, B0, C0, M0. Let's call it like this. And we know that all of them are even, all are even. Right? So if I define a new equation, A1 is half of A0, and B1 is half of B0, and C1 is half of C0, and M1 is half of M0. Basically, what will happen is I can prove that this will also satisfy the equation, no? Because I am doing half factor on every term, right? Do you realize that A1, B1, C1, M1 also satisfies?
Yes.
Because I am doing the same by 4, by 4, by 4 everywhere, no? So A1 square plus B1 square plus C1 square is equal to 7M1 square. And again, I can repeat the same step and we'll have to say that A1, B1, C1, M1 should also be even. Do you realize that this process can keep going on now?
If M1 is odd, there will be no solutions. Yes.
Yeah, there will be no solution. Same logic, right?
Yes.
So always
Okay.
we can say that there will be, this has to be even, and again I can get a new smaller solution, right?
Yes.
So that means now I'll have an infinite series of integers where our M0 is becoming smaller M1 and smaller M2. But this process cannot go on infinitely because I need the M's to be positive, which means that there is a contradiction. This is the method by which, for example, you can, Fermat also proved that this equation has no solutions. You might have heard of this, right? That it has no solutions. The way to prove it is by this argument of infinite descent, where you start off with one solution and you can show that you can make a smaller positive integer solution. And from there, you can make another smaller positive integer solution. But that process has to end. It cannot go on infinitely because there are not infinite positive integers when you are decreasing, right? So that gets you a contradiction. If you are curious about it, search for Fermat's infinite descent solution, which proves that this equation has no integer solutions. Search for that online and you will be able to get this argument, okay? I hope it is clear what we did just now.
Yes.
Okay, a slightly easier problem. Try this out. Given n arbitrary different points in a plane, prove that there exists a circle passing through two of the points that keeps the other n minus 2 points outside. There are n random points in a plane. We have to show that there will be a circle that passes through two of them in such a way that the other n minus 2 points are outside the circle.
I think I found it.
Tell me, what is your idea?
You choose the 2 points that are the closest,
Mm-hmm.
and then you make a circle with the diameter those 2 points.
Mm-hmm.
And if there is a point inside, then distance has to be smaller than the diameter,
Right.
which is impossible because we chose the smallest distance.
Correct. So the other points must be outside, right?
Yes.
So the idea here, you are correct, that is the solution. But I wanted to tell you about this particular idea also. Here, there are n points. So there are actually n choose two distances, right? Between 2 points, any 2 points. Right?
Yes.
So this is like a finite number of distances, finite number of distances. So if you make a set which has the distances between any 2 points, the number of elements in that set is NC2, right? Finite. Right?
Yes.
The main thing that you need to realize is there is something called well-ordering principle. Well-ordering principle, which says that any finite set of integers or any finite set of real numbers will always have a maxima and a minima, right? Anytime you have a finite set of real numbers, there is always a maxima and a minima, right?
Yes.
It is not necessarily true if the set was infinite. If it's an infinite set, I cannot say that there will be a maxima or minimum, right? I hope
Yes.
everybody is getting the idea. This is a very important idea because many times if you try to prove a problem, it will be easier if you look at the extreme cases, like you have just now solved this question. Only because you thought of the minimum distance were you able to do it, no?
Yes.
You thought of 2 points whose distance between them is minimum, and then you made a circle with a diameter then, diameter AB. And then the question is over. But the reason that it is guaranteed that there will be such 2 points is because this set had only finite number of distances and because of well-ordering principle. Okay.
Yes.
It is not guaranteed in general. So once you know this, the question is very easy. You just make the circle with AB as diameter. So n minus the other points have to be outside that circle. It is pretty obvious only. What I will do now is give you a few problems that I want you guys to work on. I will not discuss the solution right now. I want you guys to try it a little bit, okay? So I have like 4 or 5 problems that I will just give you as practice, okay? We can discuss the solutions in the next class, or you can send me your written solutions online also. You can connect with me on WhatsApp or email and send me your solutions once you are done. I will look at them and give you feedback, okay? So these problems, try them out. Just write them for now. This one is, let theta belongs to 0 to pi by 2 and n be a positive integer greater than 1. Prove that 1 by sine power n theta minus 1 times 1 by cos power n theta minus 1 is greater than equal to 2 power n minus 2 power n by 2 plus 1 plus 1. So this is the first problem. Just write it down. The second question is, sequence an is defined as follows. A1 is 1. An is equal to an minus 1 plus a GIF of n by 2. Is everyone aware of this function, the greatest integer function? I hope you know about the greatest integer function or the floor function.
Yes.
So this is floor of n by 2 or greatest integer function of n by 2, where n can be anything from 2, 3, and so on. What we have to do here is prove that there are infinitely many terms, in the sequence that are multiples of 7, that are divisible by 7. Tell me when you have written both of these questions. I have a few more problems to share. This relation is valid for n starting from 2, 3 onwards, okay? This one. And it has been given that a1 is equal to 1. Let me know if you have written down both of these.
I wrote them.
George?
I wrote them.
Okay. Question number 3 is this one. The sequence of real numbers A1, A2 satisfying AI plus j is less than equal to AI plus AJ for all IJ belonging to N positive for any N belonging to N positive, we have to prove that A1 plus A2 by 2 plus A3 by 3 plus AN by N is greater than equal to AN. The next one is Px is a real polynomial of degree n and A is a real number. A is greater than equal to 3. Prove that at least one number among the following n plus 2 is greater than equal to 1. There are n plus 2 numbers that I will write here. We have to prove that at least one number among them is greater than equal to 1. The n plus 2 numbers are like this: a power 0 minus p of 0 modulus a power 1 minus p of 1, a power 2 minus p of 2. All of them are followed by a modulus sign and goes on till a power n plus 1 minus p of n plus 1. So what we have to prove is out of these n plus 2 numbers, at least one of them is greater than equal to 1. That was the fourth one. And I have two more maybe that I can share, which you should work on. Two more questions, yes. So that will make the total number of problems to be 10. We have done 4 of them, and the remaining ones we'll discuss later. So have you written this down?
Yes.
Yes.
Okay. Question 5, and this is a famous theorem actually, Sylvester's theorem. It says, let P1, P2 till Pn be n non-collinear points on a plane. Prove that there exists at least one line passing through exactly 2 of these points. This is another problem where well-ordering principle has to be used. So think of maxima, minima, and stuff like that. You'll be able to figure it out. And the last problem is this one. Let alpha be a given positive integer. Find the greatest positive integer beta satisfying the condition that there exists x and y belonging to positive natural numbers such that beta is equal to x square plus y square plus alpha divided by xy. Find the greatest positive integer beta which satisfies the condition that there are positive natural numbers x and y where beta is equal to x square plus y square plus alpha by xy. And here it was given that alpha is a known positive integer. It's a given positive integer. So these problems, try it out. You should be able to get a few of them for sure. And what I would do is I will share my, okay, I think Andreas already has my WhatsApp and all. If you are done with the solutions, you can share it with me. You can ask for my contact number from Andreas and you can share your solutions with me. I will look at it and tell you if you are on the right track or not, right? So what I wanted to show you was induction and some ideas in proofs by induction. Hopefully you have learned something from this class. Hopefully it was beneficial for you guys. And if you try out these questions, definitely it will help you a lot. So try them out and let me know if there is anything that you want to discuss further. That's all from my side. You can share your solutions with me and I will check it out and tell you if there is any comment that I have to make. Okay.
Okay.
Okay. Nice to talking to you guys. I'll see you next
Thank
time then.
Thank you very much. It was very nice lesson. I'm pretty sure the students like it. I will discuss with them, and yes, so they can even send you the questions, or
They can
it
send me
could be
their
like,
solutions. If they have worked it out
yes,
on pen and paper, they can take pictures and send it to me.
yes, that would be perfect. And if one of them does correct one of the questions and the other one not, maybe what you can do is like this could be a questions that you can start in the next lesson, so
Sure.
they
Yeah.
can try them.
Yeah. Sure.
Send you the picture, have a look, and maybe you can discuss the questions for the next time.
Yeah. Sure. Sure.
Thank you very much. Thank you very
Thank you.
much.
Thank you. See you guys. Bye.
Bye.
Hmm.
Mm.